Swayam Prabha. Digital India. Educated India.
I have to write it properly because there I am taking this as 0. Or if you want to put it as omega t, I put this as alpha plus 30. You put it that way otherwise. So that is the reason why I would rather like to make the change here rather than making the change there. So specify VAN, VBN, VCN properly with respect to alpha if I am taking the limit with respect to alpha. So alpha equal to 0 is omega t equal to 30 already. So that is the reason why I am twisting this expression a little bit, because I would say it becomes omega t plus 30. If I try to look at alpha equal to 0, what is the value of this? It is sine 30 already. So it is not sine omega t where omega t equal to 0, it is rather omega t plus 30. That is how we get it basically, right? So this now has to be averaged over 1 by 2 pi by 3. This will be VDC average. Whereas if it is continuous conduction, if I am going to have continuous conduction in RL load, then I am going to have this to be 1 by 2 pi by 3 again, no doubt. But I have to go from alpha to alpha plus 2 pi by 3 because it is continuous. No matter what, every device is conducting for 120 degrees. So I have to go from alpha to alpha plus 2 pi by 3 Vm sine omega t plus 30, of course, d omega t. Right? So I'm going to have the limit set from alpha to alpha plus 2 pi by 3. I better specify the waveforms properly. We will encounter this once again for fully controlled converter where we will look at, that is a bridge converter for 3-phase, which we are going to now next take up, and there it should become even clearer, more than this. Right? So if you derive this, in all probability, I don't remember the expression, although I have used 3-phase fully controlled converter quite a bit, not this, so I don't remember it. I think it should be 3 Vm by 2 pi cos alpha, probably. That is what I remember. But you might like to check it up. Alpha equal to 62? Yeah, but I have just specified alpha. Forget about any alpha. So I am going from alpha to beta. Let alpha be 40 degrees, 30 degrees, 50 degrees, 60 degrees, 70 degrees. Doesn't matter. But I am going from this to beta. So I am generalizing it. I am deriving a generalized expression. Right? Although there what I wrote was specific. There I wrote it specifically. I would like to again point out that alpha equal to 60 we started deriving from 90. Please remember the limits we set from 90. So that's why I said you could have set this as alpha plus 30. That is also fine. But as he correctly pointed out, Siddesh pointed out, this also then should be adjusted as beta plus 30. Because beta, if you are looking at it from, alpha's point of view or omega t's point of view, better adjust that as well. That's the thing. Okay. Vm will be line voltage. Everywhere we are taking that to be line voltage because you will normally get 30 degrees ka kuch aayega. So root 3 by 2. Cos of 30 is root 3 by 2. So root 3 will come and automatically that root 3 and this root 3 will get cancelled. Please derive them. I have not derived each of them because you guys are any day better in integration and other things than I am. So please derive them. Please derive them. And put in at least some 15 to 20 minutes every day. Whenever there is a class, that particular day at least put in some 20 minutes to look through whatever happened in the class. Look through the textbook as well. That is very important because I'm not Rashid. So I will not be talking from his viewpoint. So it will be always good to get another viewpoint, how the person has derived it. Okay? That will reinforce whatever you have learned. Right. Now we are going to come to three-phase, uncontrolled, bridge, full wave rectifier, of course. Bridge has to be full wave, that's why that is redundant. Yes. Voltage across load. Yes, it is phase voltage, no doubt. But when we are deriving, if I am writing Vm sin omega t, just a second here. Thank you for pointing out. I should write Vm by root 3. Vm by root 3. So it should be Vm by root 3, but when you derive, it will come out to be 3 Vm by 2 pi cos alpha, where Vm is still line voltage. Thank you so much for pointing out. Yes, that was a mistake. Right. So, again Vm by root 3. Everywhere Vm by root 3. So, let us try to take a look at three-phase, uncontrolled bridge rectifier. Uncontrolled, 6 diodes are going to be used. That's what it means. All of them are uncontrollable devices. They are going to conduct as soon as they are forward biased. Right? So, these are the 6 devices. Right? So this is going to be the load that is connected here. Okay? I'm not going to number the devices right now because we will look at the conduction sequence and then number them. Okay? And then we are going to have one phase connected here, second phase connected here, and third phase connected here. I'm not even showing the source. Assume that I'm going to apply VAN, VBN, and VCN here. Right? Okay. Let me draw the waves for the three-phase voltages. So, let's say this is R, this is Y, and this is B. So, three-phase voltages I have drawn. So, let me name them also clearly: VAN, VBN, and VCN. Obviously, in the case of diode, whichever is most positive, that is going to conduct as far as the upper 3 diodes are concerned. Whichever is most negative, because the cathodes are connected to corresponding voltages, whichever is most negative at any instant of time, that particular diode will conduct at that point in time. And please remember, I need at least one diode from the positive side and one diode from the negative side to conduct at a time so that there is a current. Otherwise, I will not have continuous current. For example, if I assume that the current is flowing from here, it will flow through this, it will flow through this, it has to flow through the load. Load direction is like this, up to down, and it might return through this, which is C phase, or it might return through this, which is B phase. So I need necessarily one diode from the upper side and one diode from the lower side from some other leg, not in the same leg, some other leg to complete the path for the current. Otherwise, it will not work properly. So the voltage that is coming up in this particular case will be VA will be connected at the top and VC will be connected at the bottom. So I will have VAC. If I say that this is VCN connected here, this is VAN connected here. When I have shown a path like this, what is coming up is VAC. Line to line voltages come across the load when I use a bridge rectifier. So bridge rectifier will give me definitely larger amount of output, not just because both positive halves and negative halves will be transported, but also because line voltages appear rather than phase voltages appearing across the load. Right? So let us try to take a look at the conduction sequence. So whenever I am going to have this voltage VAN dominating over any other voltage, for that duration A phase positive device will conduct. Let me name this as D1. I am simply naming that as D1. Okay? After that, in the positive, I am going to have this one conducting, and after that in the positive this one will conduct. So I know for sure that I am starting with omega t equal to 0. At that point, A is not the most positive, but A becomes the most positive 30 degrees away from that. So I assume that the diode corresponding to A phase positive is D1. Okay? But D1 cannot conduct alone. Along with D1, something else has to conduct. So that something else is a negative device, clearly. So I am going to call, if I call that this is D1's conduction, I would call this as D2's conduction. I will call this as D3's conduction. I would call this portion as D4. I would call this portion as D5. And I would call this portion, whatever conducts, as D6, which is same as this D6. I am essentially numbering the devices in the sequence at which they take over. So let us say D1 takes over here. D1 will be able to conduct for some time with D6, some time with D2. So D2 corresponds to C phases negative. C phase is here. And this is B phases negative. I am calling that as D6. Then B phase takes over, which is D3. Yeah? Yeah, this is D6. This is D4. Sorry. So please note that I have written 1, 3, 5 for the positive legs, odd number, and 4, 2, 6, 4, 6, 2 for the negative devices, which are even numbers, and they have been exactly numbered in the same sequence of conduction, as they will take over when they are diodes. They are uncontrolled devices. So if I try to write what devices conduct at what time, right? Let me divide this into every 60-degree interval. I have just divided them into 60-degree intervals. So here D1 and D6 conduct. Here D1 and D2 conduct. Here D2 and D3 will conduct. Here D3 and D4 will conduct. Right? And here I am going to have D4 and D5 conducting. Here D5 and D6 conducting, then again D6 and D1, which is the first interval. You get my point? This is how they are going to conduct. And by observing this, you can directly say what line voltage will appear. D1 belongs to A phase, D6 belongs to B phase. So I should have VAB appearing here. D1 is belonging to A phase, D6 belongs to B phase, because of which VAB will appear. Here D1 is A phase, D2 is C phase, VAC will appear. This will be VBC. 3 belongs to B phase, 2 belongs to C phase, negative. So VBC. And this has to be VBA. And this has to be VCA. And this has to be VCB. This is how it will be. Right? What I am writing here are the load voltages. So this is conducting devices, and this is going to be load voltage. Am I right? And if you have to draw the waveform for the load voltages, right? This is VAN. I hope you guys remember the phasor diagrams. This is VA, this is VB, this is VC. This is how we draw per phase voltages in the phasor diagram. If I want VAB, I had to take B on the other side. So it becomes minus VB. VA and VB added together, minus VB added together, is going to give me this as VAB. Right? I have drawn it correctly, A, B, C. Because he kind of showed the hand, I thought maybe I have done the correct, incorrect thing. VA is first, then VB comes, then VC comes. Correct. So VAB. VAB will lead VAN by 30 degrees, right? From the phasor diagram, you can say that directly. Similarly, if I try to draw what is minus VC is somewhere here. So I should draw somewhere here as VAC when I add these two. VAC will lag VAN by 30 degrees, VAB will lead VAN by 30 degrees, right? So, if I say that this is what is VAB, this portion is VAB, right? VAN peak is reached at this point. VAN peak is reached at this point. Right? This is the point at which VAN is reaching the peak. So VAB should have reached the peak 30 degrees ahead because VAB is leading. So if VAN is reaching its peak at this point, VAB should have reached its peak somewhere here, even 30 degrees ahead. So somewhere in the middle of this, I should have VAB's peak. Somewhere in the middle of this, I should have VAC's peak. Somewhere here, VBC's peak. So this will be the waveform what I would get for the DC voltage of the load. What is the kind of DC voltage I get across the load? It will be somewhat like this. I am trying to say that this is the point at which VAN reaches its peak. 30 degrees ahead, VAB should have reached the peak. I have not drawn anything to scale. VAB definitely has to be having a higher value than VAN, root 3 times. No doubt. But I am basically saying that this is how the wave shape will look. So this is V load. This is going to be the V load. This is without any control on the fully controlled rectifier. Not full bridge rectifier. It's not controlled. It's uncontrolled. Full bridge rectifier. Three-phase bridge with diode will deliver this kind of a voltage if I am just having, whatever kind of load, it doesn't matter. I'm going to get a voltage like this. Now, let's try to get the expression. So, I have to integrate from this point to this point, right? And I have to integrate VAB sine omega t, whatever VAB. So, let me integrate from this point to this point, VAB d omega t. Right? That's what I need to do. And as per this, I may be able to say this is from 30 degree to 30 degrees plus pi by 3. Because every 60 degrees it is repeating itself. Please understand. 6 and 1 conduct for 60 degrees. 1 and 2 conduct for 60 degrees. 2 and 3 conduct for 60 degrees. 3 and 4 conduct for 60 degrees. 4 and 5 and 5 and 6. All of them conduct individually for 60 degrees each. The pair conducts for 60 degrees. But if you look at the individual devices, one will join hand with 6, one will join hand with 2. So it will conduct for 120 degrees, 60 plus 60. 2 will join hands with 3, 2 will also join hands with 1. So it will essentially conduct for 120 degrees. Every device will conduct for 120 degrees individually. Every pair conducts for 60 degrees. A particular combination conducts for 60 degrees. Right? So, I should say this line voltage, what is getting repeated, as far as the magnitude is concerned, it will be the same. Whether I look at it here, look at it here, look at it here, it doesn't matter. Because line to line voltage peak is the same. And it is 30 degrees this side, 30 degrees this side of the peak. So, if I try to integrate VAB, it should be integrated if I assume this is omega t and this is omega t equal to 0 point. It is starting from 30 degrees and it is going until 30 degrees plus 60 degrees, which is 90. So 60 I have written as pi by 3. That's all. And it has to be averaged over pi by 3. This is what is my output voltage. If I say that VAN 0 crossing is omega t equal to 0, VAN 0 crossing happens to be at omega t equal to 0, how should I specify VAB? VAB is 30 degrees leading. So I should write that as Vm sine omega t plus 30. Plus 30. Am I right? So, I should write this as Vm, which is the line to line voltage peak, sine omega t plus 30 degrees, and it is integrated from 30 to 30 plus 60 or pi by 3 and 1 by pi by 3. Vm is line peak. Vm is line peak. This is line voltage peak. Right?